Hi, welcome back. We're going to continue our discussion with Jacobian substitution. In the last video we talked about how we can change the base of an integral into and substitute in something a little bit nicer. So let's kind of review that real quick. We want to set up a double integral that can be used to evaluate this integral, where R is a trapezoid with the vertices, with the following vertices. So I'm going to go ahead and draw this. We have 0, 0, 5, 0, 5 halves, 5 halves, and 5 halves, negative 5 halves. So we have this trapezoid right here, or as I like to say, it's a trap. All right. Now, we're going to have to write these equations of these lines right here, so I know you know how to do all that, so I'm just going to go ahead and give them to you. So the first one has the equation y equals negative x plus 5, and down here we have y equals x minus 5. Over here, y equals negative x, and over here y equals x. Now, if I want to evaluate this integral right here, remember in this question right here, we're actually looking for a volume. Remember, because R is my base right here, give me dA, which dA in this case would be like dy dx. Length, width, and of course there's our height. There's the area of our base, dy dx. So if I want to find the volume or solve this integral, notice if I did a vertical rectangle, I have to actually set up two integrals right here. So if I draw my vertical rectangle down right here, and if I slide this over left and right, as soon as I hit this point right here at 5 halves, I'm actually on another two lines. So that means that we're going to have to use two integrals in this situation right here. Now, for the first integral, I can take a look right here. I can actually kind of start solving it right here. X plus y. I'm going to go use dy dx. I use dy dx because I'm using a vertical rectangle. That's talking about my change in y's. So my bottom y is just this negative x over here. Negative x, and it goes all the way to positive x. And then, remember, this is my change in y's. Over here, this is my change in x's. So my change in x's, this first rectangle, goes all the way from 0 to x equals 5 halves. So I'm going to, remember, we're going to move this from 0 to 5 halves. So we go from 0 to 5 halves. Now we're going to add that to our other integral, our double integral. It's still going to be x plus y dy dx. But now over here in our second integral, now I get rid of this one, my change in y's start at the bottom, x minus 5, and goes all the way to the top, negative x plus 5. And now my x value starting, going from right to left here, we're starting at 5 halves and going all the way to 5. Now, if you forgot how to write all of this, there's another video. You can check out one of my earlier videos on these. Not a problem. So, but now I'm looking at this, and I can just think to myself, clearly, this is not easy to solve. It's easy to write, but not easy to solve by hand. If we had a calculator, yeah, it'd be great, but let's pretend we don't have one. So this is not a very easy integral here to solve as is. So that's where we came up with the Jacobian. There has to be a way to write this in a way that makes it easier to solve by hand. And that's what we talked about yesterday. Or the other video, we learned how to substitute the limits of a region. Today, we are going to discuss how to change the variables in a double integral to solve using this substitution. Again, this is very similar to what we did last year in calculus and single variable calculus. And we're basically going to replace all the x's and y's with u's and v's. And again, you can look at my video from previous video to take a look at how to do all of that. We're also going to be using the Jacobian to change the variables in a double integral. So this is our rule. So this is our original integral right here. This is the OG. It's our original. Over here, this is our substitution. Now we saw things similar to this when we did spherical and cylindricals. We're just basically substituting. where we have the function x and y, we're going to change that to x and y to a function of g of u and v. So basically we are changing x's and y's. That's all this says right here. We're going to change our x and y's. This right over here, this is that Jacobian. We talked about that Jacobian matrix yesterday, Jacobian determinant that we talked about yesterday. And this is our dA. Now they have a little hat on this. The hat just means that this hat just basically means it is our new base. And this is going to be in terms of du and dv. If we let u be y, v be x. So it's just basically we're converting all of this into our new integral with, instead of x's and y's, we're going to put them in terms of u and v. Now, let's take a closer look at this dA hat. Well, what do we suppose this means? Well, the hat just means for us simply, it's just that this is our new base. It's not the same base. We saw yesterday when we did the Jacobian, we actually changed the base. When we did transformations like from spherical to, like if we did spherical or cylindrical or something like that, this circle, I can write my base here as my change in y would be from like negative square root of r squared minus x squared to positive square root of r squared minus x squared. If I were to put this in polar form, I would have a change in r would be from like 0 to r, and I would have my delta theta from 0 to 2 pi or whatever we want to go to. But notice, even though I went from rectangular to polar, we never changed our base. It was still the same base. But when we use our substitution, we're actually getting a new base. It's going to be a different shape, and we're going to see that again in a few minutes. So the new base, we're basically saying this dy dx or dy dx is going to become our du dv. We're just changing the base. We're still in terms of u and v. As a differential, the dA looks like this, where our original would become this. This is our transformation. This is the Jacobian. Whoa, that was weird. Okay. This is our Jacobian matrix or determinant, which we sometimes abbreviate just as JF times dV du or du dV depending on the order. You always want to practice this right here, writing this out. Now, we've seen this before, this transformation of when you draw the base. When we went from rectangular dy dx to polar, we would say it's r dr d theta. Well, that's kind of our Jacobian right there. We're going to prove that later on. Okay? We can prove that later on. All right. So we're going to stop this video right here, but go into video number 2, and we're going to take a look at some examples where we actually can use the Jacobian in order to solve more complicated volumes, such as this one. See you then.